Today we're going to start with an introduction to integration by substitution. The purpose of this method of integration is to be able to integrate composite functions, which brings us back to the idea of finding a way to undo the chain rule from derivatives. So we have a theorem called the anti-differentiation of a composite function theorem. And it states, let g be a function whose range is an interval I, and let f be a function that is continuous on I. If g is differentiable on its domain, and capital F is an antiderivative of f on the interval I, then we have this integral below, where the antiderivative of f of g of x times g prime of x is equal to capital F of g of x plus c. Now I know that looks incredibly confusing, but just take a minute, write it all down, and then let's take a look at just two examples. So what you see at the top of the screen in orange is just a duplicate of what we had at the beginning, at the end of the last slide, rather. So we're going to introduce this idea of U substitution. It's going to make this integral in orange look a lot simpler. If u is equal to g of x, what would du be? The derivative of g of x we know is g prime of x. And then we multiply by dx. Because I didn't write du dx, I had to put the dx on the other side. Therefore, the integral that you see above in orange can be rewritten as the antiderivative of f of u du, which would therefore just be capital F of u plus c. Still, I know that's going to look a little bit confusing. It makes more sense when we look at a concrete example. So here we go, example number 1. We're going to find the antiderivative of 3x squared times 4 plus x cubed to the 5th dx. Now, here's the thing that's causing the biggest problem. I have a binomial to the 5th power. I do not want to figure out what 4 plus x cubed to the 5th power is. That's way too much multiplying to have to do. So what I'm going to do is I'm going to take what is inside of the parentheses and I'm going to replace it with a u. So we're going to do a u substitution. So let u be equal to what's inside the parentheses. Let's see what happens. If that's the case, I want to now find an expression for du. Well, what's the derivative of 4 plus x cubed? The derivative of 4 is 0. The derivative of x cubed is 3x squared. And then we have to multiply by dx. Now here's what I notice. 3x squared dx is the same as du. Well, in the original problem, I have a 3x squared dx. So I'm going to rewrite this entire problem. So the integral now becomes this. The antiderivative, instead of writing 4 plus x cubed to the 5th, 4 plus x cubed is u, so that's just plain old u to the 5th. Instead of writing a 3x squared dx, I can replace it with a du. And now I have an incredibly simple looking antiderivative to find. This is one really short, easy to do power rule problem. Keep the variable, add 1 to the exponent, divide by the new exponent, add the plus c. The only thing I have left to do now is put it back in terms of x. So see how I have u to the 6th? I'm going to rewrite that with the u being the 4 plus x cubed. So my final answer here is 4 plus x cubed to the 6th, all divided by 6th, plus c. Or you could write 1/6 parentheses 4 plus x cubed to the 6th plus c. So you have two ways that you could write your answer. I do not care which one you use. So the process is going to take a little bit of practice. Let's take a look at another example. Before we move on, one thing I want to point out though is that you can check your answer using derivatives and the chain rule. If we were to do that for this problem, we started with 1/6 4 plus x cubed to the 6th. If I want to find the derivative of that, you would bring this exponent down, multiply to get 1, keep the base the same, subtract 1 from the exponent, and then multiply by the derivative of the inside, which would be 3x squared. And that's what our integrand was. So it turns out that we did, in fact, find the correct antiderivative. Okay, so now moving on, a second example. We're going to find the antiderivative of x to the 4th times the square root of x to the 5th plus 8. So what do you think u should be? Now, since both pieces, so to speak, we've got a piece here and a piece here, they're both polynomials, so we want to go with the one with the bigger exponent. So we're going to say let u be equal to x to the 5th plus 8. What would du be? If I do the derivative of x to the 5th, I get 5x to the 4th. If I do the derivative of 8, I get nothing, so then I write dx after it. Now that looks very close to what I have. In the original problem at the top of the screen, we have x to the 4th dx. And now I've got 5x to the 4th dx. So what I'm going to do is divide by 5 on both sides. And that's going to give me 1/5 du is equal to x to the 4th dx. Now I can use this to rewrite my original integral. So here's what we're going to end up with. We have an antiderivative sign, an integral sign. Instead of writing x to the 4th dx, I'm going to replace all of that with the 1/5 du. So constants can go out in front, so I'm going to do 1/5 there, and then du here. And I'm leaving a blank spot because I need to figure out, well, what's left. But the 1/5 du takes the place of the x to the 4th and the dx. So those two pieces are now gone. All I'm left with is a square root and x to the 5th plus 8. So I'm going to have a square root, and instead of writing x to the 5th plus 8, I'm going to write u, because that's what I chose my u to be. To do the antiderivative of this, I need to rewrite it with a fractional exponent. This is u to the 1/2 du, and then I can use the power rule. So keep the 1/5, keep the u, add 1 to the exponent to get 3/2. Oops. And then I have to divide by 3/2 and put my plus c. But we all know that dividing by a fraction is the same as multiplying by the reciprocal, so I really have 1/5 times 2/3 and then u to the 3/2 plus c. So if I clean that up just a little bit more, 1/5 times 2/3 is 2/15. And then u was x to the 5th plus 8. And then my exponent's 3/2, and I have plus c. So that would be my final answer for this problem. All right. That's it.